Well, I think we can start. Welcome back, everyone. Looks like a small class today, but we'll still get through it. We're going to finish off section 4.1, which is kind of getting over the hump of the hard content in the class, and then taking a look into null spaces if we have enough time. We'll definitely be finishing this one off when we come back on Thursday's class and start the section 4.3 on linear independence, which is kind of nice in a way. Returning to linear independence just means we're reviewing certain topics, except that our notion of what a vector space is has become a little bit larger. So some of the problems are going to feel a little bit new. Some of them will feel pretty similar. Other big announcement is we are already coming up into our third exam. It's going to be in 2 weeks from today. So it's posted here, Tuesday, November 11th. That means when I get to the Friday of this week, even before finalizing the grading, first thing I'll be doing is putting down the content that's going to be on the third exam and the review documents, just like for exams 1 and 2. Pretty much just repeating the pattern, getting through exam 3. But that's where we're at so far. That's where we're going and what we're working towards, the third exam. I think probably what's going to fit into the third exam, and we'll have it finalized on Friday of this week, is looks like section 2.2 of matrix inverses, 2.3 invertible matrix theorem, the content in chapter 3, taking determinants, 4.1, 4.2, and possibly 4.3. But I'll see if it's not going to be a rush. 4.3 is the one that's kind of on the fence. Well, any questions at all, folks, before we get started with today's work? Okay, well, returning back to section 4.1, here's where we left off. We defined what a vector space is. We looked into a lot of the canonical examples of what vector spaces could be, the ones we studied in chapter 1, and other new ones like the space of continuous functions, polynomial spaces as well. And now the major topic we're going to look into to finalize section 4.1, it's kind of a big section, is subspaces. The idea of a subspace is you have a non-empty subset of vectors that came from an original vector space V that's verified to be a bona fide vector space. If that set H has the zero vector, the one that came from V, the original vector space, and if it has the two closure properties, vector addition, scalar multiplication, then H is called a subspace of the vector space V. And a related concept that sometimes gets glossed over is that it means H is a vector space in its own right. It's just a vector space contained inside the larger space V itself. Well, we looked into couple examples. One was just the trivial subspace, the one that contained just the zero vector. It's kind of a silly subspace, but it fits all three parts here. We majorly just went over this example just to show what does going through the definition look like, going through parts A, B, and C. Sometimes we'll be given sets that are not subspaces. That means either one of these three parts are going to fail. Potentially several of them will fail, or maybe all three fails at once. But the quick thing to take a look into is, does it contain the zero vector? That's the best place to start looking because you're also addressing at the same time, is it even a non-empty subspace set? So if it contains a zero vector, well, there's something in it. You've resolved whether it's non-empty. If the zero vector doesn't belong, like in this case, your work is done. H in this problem is not a subspace of R n by n, the space of square n by n matrices, because it has the requirement to get in this set H that the determinant be non-zero. It's a set of all invertible matrices, but the zero vector in that large vector space is the zero matrix. Its determinant is zero, and so it just doesn't fit inside that set. So Z is not an H, and H is not a subspace of n by n. Well, we'll look into a few more examples just so we have the extra practice we'll need to get through the homework set. Any questions at all, folks, with this warm-up re-look at this example? Okay, because it's such a new definition, I copied it down several times on the notes, which is possibly a waste of toner. So if you printed this all out, but it's good to just see it again as we're working the new definitions. Examples 7 and 8 are pretty similar to homework exercises. I find these really tricky because H is a set. It's literally telling us it's a set, but sometimes it's hard to work with these things unless we write down what it would actually be in set builder notation. So that's going to be really our first step in both of these upcoming examples. Write down H as a set in this way. It's a set of all polynomials, so polynomials P go into this set, such that the degree is at most 3. That means if we write down a degree at most 3 polynomial, we'll have this format: a cubed t cubed plus, not a cubed, but a sub 3 plus a sub 2 t squared plus a sub 1t plus a naught. With integer coefficients, that's an interesting requirement. We'll say a3, a2, a1, a0 are in this new set, Z. I don't know if we've ever defined Z so far in this class, so let's make sure we do it here. The set of integers can be rewritten as, can be expressed as the symbol Z, which is the set -3. Let's write this down. First dot, 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 then -3, -2, -1, 0, 1, 2, 3. And if you speak German, then you'll know why it's called Z. That's just, I think Zahlen is the German word for number. So we're saying all these coefficients are integers in Z, or values in Z, so they're integers. And these are the kinds of polynomials you would have been working with in algebra courses. You might have noticed you typically had nice polynomials that you were dealing with. So we wonder, is H a vector subspace of P3? So H is the set in question. There's definitely stuff inside here. It would contain the 0 vector. If you set A3, A2, A1, A naught all equal to 0, those are integers. It's inside the set Z for sure. You'll get the 0 vector. So this is not an empty set. It's non-empty. It contains the 0 vector. And if it's a true subspace, parts B and C should hold. We're wondering if it's a subspace of P3, which just means we're going to use the ordinary operations of that space. Well, let's think about this one. To be a true subspace, both closure properties have to hold. And let's think about part B. If we generate 2 polynomials and have their coefficients be integers, adding up the polynomials, it just combined like terms. We'd be adding up the coefficients for the t cubed term, coefficients for the t squared term, and so on. And Z is a closed set. If you take integers and all you're working with is integers and you add them together, you get back an integer. You can't leave the set Z with ordinary operations of plus, minus, subtraction, division's an exception. By adding things together, subtracting them, and multiplying them, you still get integers. So part B does hold as well. Next one to look into is a closure of scalar multiplication. If you take a vector U and H, let's look into this one really carefully. We wouldn't write it a vector U if we are dealing with a function space. We might write it similar to these kinds of things. Let's start off by saying, let Q be defined by, we need to come up with a polynomial Q. Its degree has to be at most 3, so that's inside the set H. So we're tracking part C, this portion right here, just that spot of the closure property. Here's where the question becomes pretty wide open. You can put down just about anything as long as you're inside the set. I wouldn't let this Q be, say, the 0 polynomial, however, because it looks like closure should fail here. If you let Q be the 0 polynomial, well, that's not going to give us anything to work with. If you scalar multiply the 0 polynomial, it still stays a 0 polynomial. So let's go for something other than that. It can be pretty simplified. Maybe Q of t equals 3t cubed. Or, 3t squared would have worked. 3t would have worked. 3 would have worked. Those are all polynomials. I just went with 3t cubed for no apparent reason. What we're going for is a counterexample to part C of the subspace properties. And we can now say, then Q is in H. So that's the first thing we were trying to show. We found a vector. Well, we shouldn't say a vector. We found an element of H. It's in H because 3, the coefficient that we selected, is in Z. It's an ordinary integer. Now, if this was a true subspace, this space H, it'd be closed under scalar multiplication, but we could break that. We're going to pick a scalar C to show closure does not, in fact, hold. But we have to pick this really specifically. I can't pick, say, C is 2 or 0 or 5. I can't pick an integer, in other words. We'd have to pick something else. And you could be really creative. You could pick an irrational number. That would take you outside the set Z if we multiply. Or we can make a simple example. Let C equal, how about 1/2? That's a real number. It's inside the set R, so that definitely is something that would be allowed for this. So we have a scalar 1/2. It's a real number. We're looking into this part, C times U. The function property, however, looks a little bit different. It's going to be C times F, or our polynomial Q. We'll see if C times Q of an input T results in something in H. So let's take a look. We'll say then C times the vector Q at an input T would be defined to be C times Q of T. And we've done it, we've used up the function operation, this right here. So that's the whole purpose of this document, just getting familiar with writing this out. Substitute in what our scalar C is. It's 1/2 times Q, that's 3t squared, cubed. So we have 3/2 t cubed. And we can now say that C times Q is not in H because how do we get inside H? We had to pick coefficients specifically as integers. But the coefficient we have is 3/2. It's not in the set Z. It's not an integer. So it's because 3/2 is not in Z. So finally, our work is done. We showed that this closure property fails. It looks like it has a 0 vector. It certainly does if we investigate it further. It certainly looks like it's closed under vector addition. It turns out that really is true. But we didn't have to show any of that. That would have been a lot of busy work, really, because it fails spectacularly under scalar multiplication. Pick a pretty tame-looking scalar, 1/2, and you have left the set H. You no longer have a degree at most 3 polynomial with integer coefficients because 3/2 is not an integer. So our big conclusion is, therefore, H, it's an interesting set, but H is not a subspace of P3. Well, that's the conclusion on that one. Sometimes we do have subspaces, but this was 2 in a row where they were not subspaces. We'll see what happens on the next ones we look into. Any questions at the moment, folks, thinking about the subspace properties? Just to tie in those concepts, let me color code it this way. Okay, there'll be a lot of problems like, well, not a lot. There'll be a couple problems like this in the homework, which are kind of vague to get started. I think just writing down the set H as a set is a good way to begin because your subconscious is thinking of what is H really, reminds you of how you get inside the set, how you leave the set. And sometimes that's just a great way to start off these kind of problems. Here's another one along the same kind of lines, another polynomial space. We have a space P2, and H is going to be the set of all polynomials in P2 that have exactly one real root. We wonder, is H a vector subspace of P2? So that's an interesting space as well. Having exactly one real root would mean things like, say, this polynomial. H of t equals 3 minus t, 2 plus t is not in H, since t equals 3, negative 2 are roots. Real number roots, but we didn't have to say it if we're looking at the real numbers. H is going to be the set where there's exactly one real root. So this degree 2 polynomial would not qualify. H is not in that set, but if we write out a different one, maybe let's write it, say Q of t equals t plus 5, that one is an H, since t equals negative 5 is the only root. So by root, we just mean the zero of the polynomial. Negative 5 qualifies for this one, but this one had exactly 2 roots. So that's another interesting set. We wonder if it's a subspace as well. Any questions about the statement of the problem so far? Okay, these are all pretty tricky problems because if you look at the definition, there's 3 moving parts, but there's also 2 sets that you're tracking at the same time. So there's lots of stuff to get jumbled up on accident. So look through the parts carefully, look at the role the subset H and the vector space V plays on every single one of these parts as you think through the problem. And that's a great way to organize. So H is the smaller set, P2 is a larger set V. Let's rewrite H. The power just flickered in this room. I don't know if you could see that in Zoom. Let's rewrite H as it's the set. Well, it's polynomials that have exactly one real root, so we could express that P. It's inside P2, so we can write P equals a squared t squared plus a1t plus a naught. And lots of ways to express it has exactly one real root. You could just write it down verbatim inside the set. If you want something more like an equation you could write down, you might say, and P of t naught, 0, P of t1 equals 0. I was going to put a right arrow, but let's just write this out as implies t naught equals t1. So if there's, oh, forgot the 0 on that. There we go. So if we have one root here, another root here, but this is a set of polynomials with exactly one real root, we'll say the inputs were identical. So that's one way to express exactly one real root. So the question is this a subset of P2? Let's think about this one for a moment. There's 3 different parts to check. We wonder if it has the 0 vector, it's closed under addition, closed under scalar multiplication. Definitely, it's not empty because the vector Q would belong to this set. Sorry, I should say vector, I should say the element Q would belong to the set H. We don't know if it's a vector space at the moment. Silence is kind of weird for thinking time, but this requires some thought. Okay, will anyone have a place that seems like a good point to start, A, B, or C? Yeah, I would agree. This is a great place to start on this one. Does it indeed contain the 0 vector of V? The best way to address part A is you really need to write down that 0 vector of V. So what's V? V is a polynomial space P2. Well, we've written down that 0 vector once for arbitrary polynomial space Pn. Let's start by saying let We like to reserve z as a function to be the zero polynomial or the zero function. Let z be the zero polynomial of P2, the larger vector space V in the definition. The thing we have to show is it actually an H? How do we get inside H? Well, it has to be a degree at most 2 polynomial, so you can pick on any values you like here for the coefficients. But critically, it has exactly 1 real root. But that's not how the zero polynomial works. The zero polynomial, by definition, is 0 for every single input you put inside here. It has infinitely many real roots. So there's a problem already. We can say, then z is not an NH because z of t equals 0 for all inputs t in R. Having 2 roots look like this. This polynomial h had 2 roots, 3, -2. H itself is not in the set H. The zero vector has infinitely many real roots. Pick any number, 5, pi, e, square root of 2. It's always going to come out as 0, being the zero polynomial. So H being the set where it has exactly 1 real root tells us the zero vector is not an H. And so good call. We could have looked and worked really hard into the closure properties, but the whole problem ends once we notice it doesn't contain the zero vector. We have to write down the conclusion, so we'll say, therefore, H is not a subspace of P2. Then the whole problem ends right there. So P2 is a larger space, H was the subset, which is not a subspace. Well, any questions, folks, with that so far? Okay, so that's like 3 in a row where they're not subspaces. The next one turns out it is a true subspace. So we'll go through all 3 parts, A, B, and C again. So far, what the examples have all been about is just studying how these definitions work. Then we're going to put these into good use in section 4.2, where we'll come up with an important subspace, well, several important subspaces, the null space and the column space. Actually, column space came up already once this semester when we were all the way back looking into span. So it's going to be kind of a welcome reminder of what is a column space in the first place. So let's take a look into this once again. It's a tough definition, so I think lots of practice is always a good idea for this one. That's why section 4.1 is in the schedule for 2 days instead of the typical one. And here's our new set we're going to be looking into. The vector space V, if you'd like, you could just write out V. I'll write it out as C -1, 1, is our space of continuous functions. So let's just rewrite this as a reminder. This is the vector space of continuous functions on domain -1 to +1. And there is so much you can say about this as a vector space. It's rich with structure. An entire discipline, functional analysis, can be spent many weeks just studying this one vector space. Loads of things going on with it. But all we're looking here into is, can we write out this set H and let it be an actual bona fide subspace of this complicated structure here? So here's the larger set V in the definition. The smaller set H is this one. And it has this interesting condition. F is in C -1, 1. And all F has to do to get inside this set is it has to be equal on the boundary points. So because it's inside C -1, 1, it's also a continuous function. But we already investigated that we know for sure scaling a continuous function is still continuous, so we don't have to reiterate that as part of this problem. And we know adding continuous functions gives us a continuous function. So again, for this problem, we wouldn't have to reiterate it. We'll take those ideas for granted. The major thing is, will we get this feature to hold? And if you're thinking all the way back in Calculus 1, if you add one more condition, that these functions are differentiable at the same time, then this would be the subspace of functions that satisfies Rolle's theorem. So that's just a really interesting little side fact about this. Rolle's theorem was where you have something that goes like this. Go from -1, that scale already looks weird. Go from -1 to +1, make the function match at the boundary values. And then you'll have a absolute maximum or absolute minimum somewhere, was the idea with Rolle's theorem. So to start this one off, we're going to investigate all three parts. It turns out this one really is a bona fide subspace, which means there's actually a lot of work to show. Let's go carefully by looking into the zero vector. Part A of this kind of proof that we're looking into is tricky because there's two sets being mentioned here. You have to start by pulling the zero vector of V. We've essentially already done that today. The zero polynomial is the zero vector of V as well, -1, 1. Let's just reiterate it here. Let's say, let Z be the zero vector of C -1, 1. Then what would that mean? This just means then Z at T equals 0 for, we should mention the domain values, all T in -1 to +1. So we've got the zero vector listed, redefined, probably the third or fourth time we defined it. But what we need to do with it is explain why it's also an H. The explanations are what makes the homework in this section tricky. To explain why it's an H, we have to go back to the set. To get inside the set H, we have to satisfy this condition here. So this is the set membership condition. But that's not so bad because the zero vector has one output, 0. So it automatically is going to match when we put in an input of -1 and an input of +1. We can say just really briefly, then Z at -1 equals 0, which is equal to Z at +1. That's a good thing to write down because it reminds us we're talking about this, matching at the boundary values of the closed set. So Z is in H. And part A is done. We took the zero vector of the set C -1, 1. We showed it's inside this interesting subset H. We also showed because it contains the zero vector, it's also non-empty. So we get that as a bonus as well. Any questions at all, folks, maneuvering through part A? Okay, feels pretty abstract because again, we're not looking into ordinary vectors whatsoever. We're pretty far away from chapter 1 material where we're in Rn. But thinking in terms of sets, all we need to do is carefully verify this for vectors when we look into vector additions and vectors when we look into scalar multiplication. You could call the vectors U and V, but it would look really weird in this context. If you're dealing with polynomials, P, Q, R are the typical values, maybe S. If you're looking into functions, F, G, H are good things to write down for your vectors in this case. And matching up the context is just making it a little bit less confusing. So anything you can do to make this more concrete is a good idea. So to start this out, I want to grab two vectors inside the set H and a scalar all at once. Because F is already listed here, I don't want to call my new vectors an F because then it would have a double meaning. It might make it a little bit visually hard to track the definition of getting inside the set H. So let's start off instead by saying let G and H. Those are going to be my two vectors that we picked, which look like the typical way we'd write functions. Let's GH be in H. So we took two vectors from there. That's this part of the definition. And let C be in R. So we're doing this part as well. We're just grabbing the three objects that we're going to need to run through both parts B and C. But it's a really good idea because a set membership condition is sometimes kind of hard to track. There's just lots of symbols you're staring at on this page. The moment you said G and H are in capital H, let's write down this. This means G at -1 is equal to G at +1. That's just the set membership condition for the function G that we pulled out of the set H. And H of -1 is equal to H of +1. Well, any questions at the moment, folks, writing down those two equations? Okay, at the moment, most of this is really just set theory working with functions simultaneously. If G and H came from the set H, that equation holds for it. So all we're doing is swapping F with G, writing down the same equation, and same with lowercase h. Now we're going to move through parts B and C. So my sentence goes then, here's the part B. We have G plus H in H. That's a bold statement, right? We're setting down exactly what we want, this right here. We have to justify it, so our justification is going to be down below. But this is not a bad strategy. Track the definition basically verbatim, because then it's going to remind you what you need to show. We have G plus lowercase h and capital H because what is G plus H? We have to pull out the function operation and run through this. There'll be a G here and a lowercase h here, and an input fused X, no harm done, but I'll use T since it's more common in the reading. So G plus H at T, recall this is just one symbol, the new function that we want to show as an H, and this over here is going to be how it's defined. This is defined to be, let me backtrack one spot. You could put the T in here, but in terms of the set membership condition, it's probably wise to just start with -1. We're trying to show we're inside the set H, so we have to satisfy this equation up here by the red dot. So G plus H of -1 is G at -1 plus H at -1. And we can make another substitution. We've already written down G at -1 is equal to G at +1. H at -1 is equal to H at +1. So we get that equation for free from the prior ones here and here. Then G at 1 plus H of 1, just unwind the function operation going from right to left where X is 1, and we get G plus H at +1. So all we had to show is that if we put in this input, we get G at H plus H at the other input, +1. So we're back to that equation here. And that justifies the bold statement we made that G plus H really is inside H. It satisfies the set membership condition. So that's part B in a nutshell. Any questions at all, folks, running through that portion? Okay, so part A is done. We have the zero vector. We just showed closure holds at the same time. Grab any two functions inside the set H, add them together, and this property holds. We showed it by just following that long track of equalities. And so next we can say, and here's part C. We need to show we already have a vector in H. Well, let's just use G again, that the scalar multiplication of C times that vector is also in H. So we're on that part. And let's just state what we want like before. And we have C times G is in H because Really the same kind of idea as before. Let me scroll just a little bit down. To get inside the set H, we just have to satisfy this condition. So we take the function C times G. Here it is. We put in the input, -1, the left boundary point. Our job is to show it's C times G at +1. So the whole entire thing, CG, is just playing the role of F here, and it'll be playing the role F here on the right-hand spot. And same idea with what we did with G plus H. Next, the function operation. It's always good to call this up because the steps kind of look confusing on why we're writing it out in a particular way. The definition of C times G is C times G at the input 1. So this looks like C times G at 1, -1, that right input we have here. Then go back to what we said at the beginning. Being inside the set H means G at -1 is equal to G at +1. Then back down here, undo the function operation. This is the function C times G at +1. That's what we were meant to show. The entire function C times G is just playing the role of F in the original definition of the set H. So this shows part C holds as well. We have the zero vector, closure under vector addition, scalar multiplication we just showed. And so we're done. This shows, therefore, H is a subspace of C, -1, +1. The subspace has a lot of different names because it's been studied so extensively. If you know you're taking probably a lot of math or maybe a lot of applied mathematics, this is probably going to come up again at some point. So it's good to introduce what it's really called. This is called a Banach space because of all the amazing different properties it has. It's something that's been studied in a lot of different ways and a lot of different points of view. And it's our one big example. There'll be another one of an infinite dimensional vector space. Lots of pretty interesting things and weird things happen in this vector space. But any last questions or comments, folks, getting through this example here? Okay, this is a pretty heavy problem. We went through abstract definition, all three parts. So our next problem is just going to be kind of a lighter one. The definition isn't here, but we've looked at that definition pretty extensively. So let's think about this question. It's a pretty confusing one in a certain sense. Is R2 a subspace of R3? Let's think about that one for a moment. Doesn't hurt to pull in the definition. While we're thinking about it, let me drop in the definition so we can ponder that. Okay, well, how do folks feel about this one? What would you all say to this question? Do you feel like R2 is or is not a subspace of R3?
It is.
Looks like some for it is in class and over Zoom. Anyone with a contrary point of view? Okay, turns out, and I understand the sentiment entirely, we'll say some words on it, but R2 is not a subspace of R3. And that feels really, really weird. So there's a certain notion where you can make it a subspace, but that's going beyond the definition of what we're looking into here. So example 10 turns out to be kind of a trick question in a certain sense. We tend to focus on parts A, B, and C really critically when we're thinking about subspace. And you might be thinking of this geometrically. R3, three-dimensional space, it can certainly fit a plane, right? And that's what R2 is. the x1, x2 plane. This is just the x1, x2, x3 plane. So why is it not a subspace? There's something in the definition that's preventing it from being one true subspace. Anyone see what part of the definition it is? Absolutely. When we go to track, say, this part A right here, the zero vector of V, what is it? Let's write it down. V is R3, and we can say the zero vector of R3 is, we often wrote it down this way in chapter 1, but if we wrote it down more specifically, it'd be 0, 0, 0. And, well, it has 3 entries, right? R2 is a subset, is a set itself of all vectors with specifically 2 entries. This tells us, or this shows, that zero vector is not in the smaller set R2, since this set consists of vectors with exactly two entries. So if you felt like R2 is a subspace of R3, it turns out it's not, but your geometric thinking isn't entirely wrong either. There's more to this story, but this is looking at the definition, answering the question verbatim. It's actually not a subspace. But here's the next part of the story. Any questions at the moment with the conclusion to example 10 first? Okay, let's take a look into this a little bit more carefully. We have 2 spaces, R2 and R3, and we look into R2, that's just the x1, x2 plane. R2, a typical vector, let's just call this our typical vector. U would be equal to a U1, U2. For any values of U1, U2, any quadrant you would like to put it on, or any axis. Then if you go to the larger space R3, this is where my artistic talent kind of fails me, but it's usually drawn in this kind of way. So here is the positive x3 axis. The negative end is going off that way. Here's, not x3, but x1. Here is the positive x2 axis, and the negative end is going off this way, but I won't put it in too many dots. X3 axis goes this way, and a typical vector here looks like this. V equals x1, x2, x3. But we can define a pretty interesting linear transformation. It will go like this. Map from R2 into R3. Let me put down a symbol just for parallelism. Transformation T, going from that space to that space, will be defined this way. T is going to take an input, U. More specifically, the input will be a U1, U2, and it's going to map it to U1, U2, 0. So if we do that transformation, this vector, wherever it was, just gets mapped down to over here. So here's T of U. And it's in this interesting sense that it's in this point of view, R2 kind of fits inside of R3, not as a subspace, but through a linear transformation. This linear transformation has a lot of nice properties as well. I'll leave it to you to verify. T is linear. Let's use a more official looking pen. So property 1 is that T is linear. Property 2 is going to be the idea that T is 1, 2, 1. T, well, it's not exactly on 2, right? Because the entire space is R3. T is not on 2. But if you make another restriction, if you say the codomain of T is, let's say it's not R3. Let's make the codomain of T be the set V equals x1, x2, 0, such that x1, x2 is an R. Then we get to say one more thing. T is now on 2 with this change. T is on 2 and becomes an isomorphism. Meaning anything you do in the domain space R2 would be equivalent to not doing stuff in R3, but doing stuff in this specific vector space. We just insert a 0 inside to make it fit geometrically into R3, but now it's an isomorphism. R2 algebraically is completely equivalent to V. So that took a lot of forcing, right? To make it be a true subspace, it didn't exactly work out. You would have to start with R2 is that. It would have to have 3 entries for it to be a true subspace of R3. But if you feel like it kind of fits into a certain way of thinking, this is the true story about it. You can force in a linear transformation, change the codomain from R3 into something more like this, and these spaces are now identical algebraically. But the big takeaway from the whole thing is to be a true subspace, it has to be a subset in the very first place. That's a major thing that goes wrong. And so example 10 is kind of a weird one, just another way to look into the subspace definition. And another way to just talk about isomorphisms, because we'll look into them in big way when we get into coordinate systems in section 4.4. So we'll define a particular isomorphism to simplify a huge amount of linear algebra. But any questions or comments at the moment, folks, concluding this example? Okay, well, this is the last part of the notes. And a big pattern so far with chapters, I'd say 3 and 4, is that theorem 1 is kind of like the major theorem that you're going to use quite a bit throughout the chapter. Theorem 1 is the big one for chapter 4. We're going back to what we dealt with spanning in the prior chapter 1. We'll have it redefined here. Really, it's the same definition, except we make this change. V can now be any vector space. So it can be a space of polynomials. It could be continuous functions, anything whatsoever. It could be R4, something more concrete. If we take a set of vectors and span them, all we really mean is the set of all linear combinations. This is what the linear combination would look like. And we allow the scalars or the weights of that combination to be any real number whatsoever. So that's the span of a set. Now, theorem 1 is a fantastic theorem. The proof of it's not too hard. It's just a lot of writing. I'll leave it up to the reading on that one for you to take a look into. But the statement is massive. If you take any set of vectors in a vector space V, span them, you'll get a subspace of V. So automatically, spans are subspaces, is what this is saying. The span of a set becomes a subspace. That makes certain problems really, really fast to solve. That's the example 11. W is the set of all vectors of this form. We're returning to something more concrete. This is an R4. We wonder if it's a vector space. Well, we don't actually want to track all of the vector space axioms. That would be a huge operation, a big undertaking, and it would be pages of work. A bigger way to tackle this is to think in terms of subspaces instead. If you can show that W is a subspace of R4 because there's 4 entries, then the work is majorly simplified. So that's our strategy. Show W is a subspace of R4. The reason that helps us is subspaces themselves are bona fide vector spaces in their own right. So this can help us out a lot. But then the subspace definition is also big. There's 3 parts to check. I mean, it's not hard to see the 0 vectors inside the set. Pick the parameters A, B, C, all equal to 0. You've got the 0 vector. But doing the vector additions, the scalar multiplication properties, it's a lot of writing. If you could write it instead as a span of a set of vectors, your work is automatically done right at that step. You just cite theorem 1. So that's how we're going to tackle example 11. And the way we do it is really going back to the notions we've talked about before. This is, in a certain sense, a way of writing down a parametric vector form. The parameters would be the actual scalars. The vectors are v1 through vp. We could take this set V and rewrite it in that way. Our work is done. So let's give this a try. W, the thing we're going to show as a subspace, is equal to, in parametric vector form, let me fix that brace. They're not coming out right today. One more try. There we go. There's parameters A, B, and C. A, B, C are in R. Then let's just pull coefficients. For the A parameter, we'll have coefficients 1, -4, 1, and 0. For parameter B, coefficients go 3, then 3, 0, 0. And for parameter C, going into this column, we have coefficients 0, 1, 0, 1. So this entire vector is just the linear combination of this. If we did the scalar multiplications, the vector additions of all this stuff here, we get back to this vector that was given to us in the problem. You can't always do that. So we'll see in the very next example where it goes awry, where this would fail. But the giveaway on this is everything is just a multiple of some scalar value and a parameter. Something that doesn't work would look like this. That +5 is a dead giveaway. Something's going wrong in this problem. So the moment we can write that out, we now have that W is equal to the span of 1, -4, 1, 0. Now we use commas when we write down the span of a set of vectors. This is just more the linear combination that we exhibited in the prior step. So taking it one step further is just a way to see how does theorem 1 work directly. Write it as a span. The vectors we're spanning go, the first one we put down, then 3, 3, 0, 0, 1, 0, 1. And our work is done immediately at that step. We can say, therefore, W is, the question was if it's a vector space, and the answer would be yes. W is a vector space because it is a subspace of R4 by theorem 1. So that's a fantastic theorem. It says, if you can write down your set as a span, there's nothing further to show. A lot of this was just writing down the tall vector. There was not a lot of writing or thinking to do about this one. So it saves us a lot of time. Well, any questions, folks, about theorem 1 at the moment? Okay, theorem 1 is going to be cited and used in a lot of different kinds of places. And we've been mentioning parametric vector form in a lot of different contexts as well. These column vectors turn out to be the major thing that we want in a lot of problems in chapter 5 when we're getting into eigenvalues, eigenvectors. So the skills of writing things down in parametric vector form, finding solution sets to homogeneous system of equations, those are going to be the major skills that we're going to put all together in the next chapter 5. Well, we'll see how this goes wrong next, but any last questions or comments? Okay, so one more example, and we made it through section 4.1. Same question for this set here. W is a set of all vectors of the form x1 plus 3x3, x1 minus 2x2 plus 5. That one is an odd one out. And that's a problem in a lot of things. This would be an issue for trying to find a linear transformation. We found that this would mean there's a problem mapping with a zero vector. We can automatically say it's nonlinear because of that plus 5. On the third row, the x3 is not a problem. But you know what's weird about this vector space W is it does contain the zero vector. For example, that's a good place to first look. If we look into that, we're wondering if it's a vector space, and the same idea, we're going to see if it's a subspace of R3. Let's write that down as a first thought. We will check if W is a subspace of R3. The first thing we're going to do is turns out to be kind of a misadventure, but it's good to put down on paper because sometimes it's something you might do in homework. This is a pretty common mistake. So we're going to check if W, let's redefine the set. W is the set of all vectors of the form x1 plus 3x3, x1 minus 2x2 plus 5, x3, x1, x2, x3 are parameters that can take any value in R, contains the zero vector. It might or it might not. It just depends on how this is all arranged. So let's start by saying if the zero vector, we're thinking the zero vector of the space R3. So the zero vector 0, 0, 0 is in W. Then getting inside W would mean the zero vector 0, 0, 0 would be equal to, let me fix that color coding there, x1 plus 3x3, x1 minus 2x2 plus 5, x3. We're now looking at vector equality, and we can equate things on a row by row basis. Across entry threes, this would tell us then 0 equals x3. And that's a value that we could pick here to get the 0 on that entry. If 0 is x3, well, that part is gone. We have 0 equals x1 plus 3x3, which implies 0 equals x1. So x1 is gone, x3 is gone, and what happens in row 2? We'll have 0 equals x1 minus 2x2 plus 5, but x1 went to 0, so now we have 0 equals negative 2x2 plus 5, and we could solve for x2 on this one. This implies x2 is going to be, let's see, subtract 5, divide by 2, 5 halves. So there's a way to get the zero vector. You pick 0 is x3, 0 is x1, x2 is 5 halves, and you put the zero vector inside the set. This is consistent as a vector equation, in other words. And that's unfortunate because it's still not a vector space, but this is an important thing to check out. Depending on the algebra, this might have been the slickest approach because we would have seen the zero vector is not inside the set W, then our work is done. But it's good to see when the algebra goes awry. It just didn't support the narrative that we were trying to write down. We have, this shows the zero vector is in W as well. So we have to look into other issues here. We're trying to show if it's a subspace. If it is, then our work is done. But I still say that that 5 is going to cause a big problem. So let's look into another subspace property. We can look into, does closure of vector addition fail? I believe it would. If you took two vectors of that form by the red dot, added them together, you would get a plus 10 right there. Instead of the plus 5, that would break the format, and you would leave the set W. But I think scalar multiplication might be just a little bit easier to show. So let's try it with the scalar multiplication side. For the next part, let U equal, I want this vector that comes out of W, so I want to put it in this particular format. U1 plus 3 U3, U1 minus 2 U2 plus 5 U3. Because of the form that we wrote down U, automatically it's in the set W. Then U is in W. So we're trying to break scalar multiplication, which means we need to grab an arbitrary scalar. Probably not 0, because if we scale this by 0, we just get the 0 vector. It's already in the set W, so we need to pick something else. Definitely don't pick the scalar 1, because it just gives you back the vector U already in W. How about a scalar 2? Let's scale this vector U by 2, see what we get. Then 2 times U is going to be equal to, scaling by 2 is just going to multiply all 3 rows by 2. Distributive law is going to give us 2U1. I'm going to associate in this particular way. Sure, it's going to be 6U3, but we can rewrite that as 3 times 2U3. The reason I'm being really particular in how I'm writing this is because I want to show that these elements match up to that algebraic form on how the set W was defined in the very first place. Let me reset the yellow so we can focus on that different spot. Scale by 2 through here, and we get 2U1 minus 2 times 2U2 plus 10. And then finally, it's going to be 2 times U3. So all those values are the things that we need to get inside the set W, but the 10 is the problem. The moment we have a 10, we've broken the definition of the set. There had to be specifically a 5 right there, and we have a 10. This is enough to show that 2U is not an H. So closure of scalar multiplication fails here, all because of that plus 5. If it was, say, a 5x3, you could decompose this into the span of 3 vectors, just like we did before, and it would automatically be a subspace of R3. Here, we have a closure property failing, so we can conclude immediately, therefore, H is not a vector space. It's not a subspace of R3, and it's not a vector space either. Closure fails in a major way for this particular set W. Well, that's turned into a longer problem than I thought. Sometimes this zero vector check works out. It'd be something I would do on scratch paper, and if it works, that's awesome. But other times the algebra works out not nicely for us, and you have to do something else. Show a scalar property fails. So these are the last couple problems that you'll be taking a look into in section 4.1. If you have vectors of this form, try to use theorem 1. Spot the things that are going to make it go wrong. And these are the steps that would support how to maneuver through those cases. Well, any last questions at all, folks, before we close out the section? This came out to 12 pages. It's taken a moment for this one to save. There it goes, almost. The fan is speeding up on this computer. Okay, that worked a little bit hard. But we made it. The major ideas we're going to take away from this are ideas about closure, subspace, the different kind of vector spaces we were looking into. But once we go to section 4.2, it kind of feels like a little bit more familiar territory. 4.2 is in fact a section we could have done in chapter 1. We just didn't want to make chapter 1 gigantic. The major thing we're going to be studying now will be called a null space. The null space is going to be another one of the major objects we'll be looking into in linear algebra. We'll also formally define what the column space is. We looked into it briefly back in chapter 1. They're defined in terms of sets. The null space of an M by N matrix A, it could be square or non-square, is just simply stated as null A, kind of in a function format. That's a set of all solutions to the homogeneous equation, AX equals 0. So we're going back to chapter 1 material directly when we studied that equation. I think that was section 1.5, if I remember correctly. So as a set, the null space of A are set of vectors X and Rn that satisfy AX equals a 0 vector, the full solution set of the homogeneous equation. This is a pretty interesting space, and it turns into, later on, we'll check that this is in fact a subspace of Rn itself. So now that we have a notion of what subspaces are looking like, these are just two big examples of subspaces we're getting into next. So let's write that in the notes. This is kind of how 4.1 connects to 4.2. There we go. So these two are the major subspaces. So first, what we'll look into is to check if we have a vector X that's really the null space of A. These are two kind of different type of problems, but the part A to this problem is kind of a fast problem to get through. If X is inside null A, this could be an exam question in its own right. All you have to show is what happens when you take A times X. So it's really just a matrix multiplication problem. Also, it's just another set theory problem as well. X being inside the set null A means it has to satisfy that set membership condition. A times X has to come out as a 0 vector. So that's the part we're checking. So A goes 1, 0, 2, 1, 3, negative 4, 0, 1, 0, 5. We multiply it by the vector X, 1, negative 1, 5, 4, 0. The output is going to be a 2-entry column vector. And to multiply through, we'll get 1 times 1 for a 1, minus 2, so we're at negative 1, plus 15, so I'm at a 14, plus 0, plus 0. So first entry is 14, and really at this stage, the work is done. Sure, we'll finish this out, but it's critical. It didn't come out as a 0 vector, and so we already have a conclusion. We can say, therefore, X is not in the null space of A. Because we already can show this is not equal to the 0 vector. It's weird to leave it hanging, so let's keep on computing through this. For the second entry, we'll have 0, minus 1, minus 20, so I'm at negative 21, plus 4, so I'm at a negative 17, plus 0, so negative 17. So that vector X was way off. It didn't get us anywhere near the 0 vector. So X itself, we say, is not in the null space. The null space is just the collection of all vectors that sends you into the 0 vector. And we can say a lot of interesting things. If A is a square matrix, for example, and the columns are linearly independent, then AX equals 0 only has the trivial solution. There should only be one vector inside there, the 0 vector. But we know the 0 vector is the trivial subspace. It's a subspace and a vector space in its own right. So part A is kind of an interesting problem. It could be an exam question all on its own. And word of warning, it's actually tricky because it's more of a vocabulary check type of a question. You have to know x being a null A just means you're taking A times x and see if it results in the zero vector itself. So that means you're in null A, that means you're not inside null space of A. More common question, part B, also a good question on exam 3 is to find the null space. And that's what we'd be doing next. The cool thing about the null space is no matter what matrix you're looking into, you can always write the null space as a span of a set of vectors. Even if the zero vector is inside there, you can write the zero vector as a span of the zero vector. That's a weird thing to write, but it would qualify. But this then connects back to section 4.1 because we can always write the null space as the span of a set of vectors. We can go back to this really powerful theorem here. The span of any collection of vectors is an automatic subspace. So this tells us already together the null space will be a subspace of R5. We just have to compute it. But really all we're doing it when we write this out is we're finding the solution set to AX equals a zero vector in parametric vector form. So that terminology, that technique, it just keeps on coming back. And this is its next showing, aside from the ways we've seen it come back in chapters 1 and 2. We'll be doing parametric vector form for these kinds of solution sets as well. And that's when we're going to be finding eigenvectors. In fact, back in chapter 1, we wrote them down this way as well, because these, for the right matrix right here, would be the actual eigenvectors that we're looking for in the first place. So that's the role that the null space is going to play in chapter 5. And that's why we've been paying so much attention to the parametric vector form. This one takes a minute to write out. We want to write it out carefully. It's a bona fide review problem, but we'll take a look into this when we come back on Thursday's class, so it won't feel like we're rushing through that second part. So we've introduced the null space. It's just connecting back to the homogeneous system of equations, and we're going back to parametric vector form. This is what linear algebra looks like in a lot of cases. It feels like you're doing the same old techniques, but just new ideas, new notations and definitions get put on top of it. Any last questions at all, folks, before we call it a night? I guess it's not quite night. Call it a day. Okay, well, have a great afternoon, folks. We'll come back here finishing off 4.2 when we come back next class. We might take a look into section 4.3, but probably won't get very far into that next section. Well, we'll see you all next time. Thanks.